I hope everyone's having a great evening. I am Mr. Ace. Thank you for joining me. We're looking here at the tangent function. The tangent function is an odd function, and it looks basically like this. And you have an f of x or a y is equal to a tan x. The reason why it's odd function is because it has origin symmetry. And why would that be the case? If you were to look at something like this as your function, it would have a odd test characteristic. Minus f of x would equal to f of minus x. And you can easily verify that on a calculator. You don't have to use a calculator, just pick an easy value. If you take tan of 45, it's equal to 1, but now do minus tan of 45 and that'll be equal to tan of a minus 45. This right here is a 1 in all instances and you get a minus 1. This right here is a minus 1. And you can even check that on your calculator. Just check it on your calculator on the side, you'll see it to be the case that indeed it will be an odd function. How do you demonstrate a function f of x is equal to tan x in terms of its graph, but doing it in a more comprehensive manner? Well, again, you have to pick some values. You can pick 0, you can pick pi, and you can pick 2 pi. When you go on this side, you have a minus pi, and when you come over here, you have a minus 2 pi. When you do tan of 0, classically it's a 0, so you have a good x-intercept here. Remember, in all instances, tan is always sine or cosine. X, sine x or cosine x, whatever value sine is a 0 for, it will zero out your entire tangent. Sine is always 0 at pi, 2 pi, minus 2 pi, therefore tan must also be that, and it'll zero out your entire tangent function. Now, wherever cosine happens to be a 0 in any of the values for the cosine function graph, then you'll have a vertical asymptote develop. Cosine is always 0 at the pi over 2 multiples or 90-degree multiples. If I'm doing pi over 2, 3 pi over 2, this is 90, 270, minus 90, minus 270, then in these instances you'll have a vertical asymptote develop for the tangent function. And that exactly is how your graph will look. But now let's look at the x-intercepts. As I've told you, wherever sine is a 0, tan is a 0, well, it's a 0 here at these dots. Right over here. Therefore, you can now start drawing it. I've told you earlier that tan of 45 is equal to a 1, which is a positive value. You can use that as a guide. You're looking right here and your curve will end up coming like this. And then it'll be exactly the same between all of these asymptotes, exactly the same. Here you'll come up to here because your graph ends. Here you would have had a curve coming down, but it's visible over there. And that right there is your tangent graph. And you'll see all the parts. You'll still have a 1 over here and a minus 1 over here, except these are all your 45-degree angles. Tan of any of the 45-degree angles, 45, 135, 225, 315, will always show up as either 1 or a minus 1 on all of these graphs. And that's how you'll see them. Because tan of 45 is a 1, but tan of 135 is a minus 1, tan of 225 is a positive 1, and then tan of 315 is a minus 1. That's exactly how it's going to be. But your main landmarks here are exactly what I'm showing you here. Wherever sine is 0, you'll have a tangent 0. But wherever cosine happens to be 0, because it ends up in the denominator for tangent, you end up seeing a vertical asymptote, and that's at all of these 90-degree angles. What is the range of this tangent function? The range for each of these sub-curves or little wavelets is always minus infinity up to infinity. But what is the domain? Well, the domain is not minus infinity to infinity. Technically it can, but then you have to throw in exceptions, and I can say x is an element of all real numbers. Now the exception is this: x cannot equal to anywhere you have these vertical asymptotes. I'm seeing a vertical asymptote here at 90 pi over 2, but then the next vertical asymptote is 270 or minus 90 plus or minus pi n. That right there is, it's either 180 on this side or 180 on this side by multiples of pi, and you'll always hit the vertical asymptotes, and those will be your exceptions. Beyond these exceptions, any x-axis value will be in your domain of the tangent. That right there is your tangent function. Before we end this video, let's very quickly look at the inverse of tangent. Very quickly, in just one limited area, we're looking here from pi over 2 to minus pi over 2, positive 90 to minus 90, we know the tangent looks like this. If you were to focus here, horizontal lines will only cross at one point, anywhere over here. Therefore, it passes the horizontal line test. Therefore, this function should have an inverse. And how do you calculate the inverse? Well, look right over here. Y is equal to tan x. Flip the y and the x around. X is equal to tan y, and now calculate for this y. Y is equal to inverse tan of x. or y is equal to arctan of x. These are your inverses for your tangent function, and they have very good applications and usefulness in calculus. Very quickly, we can show you just a quick application of how this would play out. Find cosecant of arctan 1 over 3. How would we do that? Well, you have seen videos like this before on this channel. Utilize this to map out a triangle. In terms of a certain degree theta, tan is always equal to opposite or adjacent 1 over 3. You must fill this side. 1 plus 3 square. 1 square plus 3 square is a tan, and root of that is a root 10. Cosecant of a theta is going to be what? The definition of cosecant is hypotenuse over opposite. It'll be root 10 over 1, and it'll be root 10. So you can see how the inverse tan played right over here to help you find another function with regards to a common angle. That right there is a very useful application. But that's about all I want to show you in this video, the main focus being the tangent function and its graph. Thank you for watching. Have a nice day.